All right, in this lesson, we are going to talk about the key attributes of rational functions. And so in particular, we're going to talk about the point of symmetry. We're going to find max and min on intervals, and we're going to find intercepts. Okay, so starting with the point of symmetry, rational functions have rotational symmetry. And so that means they have a point of symmetry, not an axis of symmetry. And so if I were to just graph the parent function, he has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. He has one branch in quadrant 1 and another branch of the function in quadrant 3. And so if I were to rotate this function about the origin, it would look exactly the same. So let me see if I can make this happen. So rotating, he looks exactly the same. And so that's why it's rotational symmetry. If I were to reflect it, he would be in quadrants 2 and 4. So it doesn't have an axis of symmetry like our quadratic or absolute value. Okay, and so the point of rotational symmetry, in this case it was the origin, but it's actually where your vertical and horizontal asymptote intersect. And so if you move the vertical and horizontal asymptotes, wherever they move to, their intersection is your new point of symmetry. And so if I were to, let's say, move the vertical asymptote here and then the horizontal asymptote here, I would have my function symmetrical about this point, this new intersection point. Okay, so we just need to find the asymptotes using our transformation in order to find the point of symmetry. So here it asks us to find the point of symmetry. And so this is our parent function. So vertical asymptote, still x equals 0, horizontal asymptote, y equals 0. And so our point of symmetry would be 0, 0. Okay, this next one, it has been moved left 3, and so our vertical asymptote is x equals -3, and then it has moved down 5, so our horizontal asymptote is y equals -5, and so our point of symmetry would be -3, -5. Okay, the x goes in the x spot, the y goes in the y spot. Just thinking about where these would intersect. And so let me get a sketch. And so at -3, we have a vertical asymptote at x equals -3. And then at y equals -5, we have the horizontal asymptote. And so that's why the new point of symmetry would be -3, -5. Even though it's also reflected, it's still going to be symmetrical about that point. If I were to rotate it about this point, I'd still have a branch in quadrants 2 and quadrants 4. Okay, this next one has not been moved left or right, and so the vertical asymptote is still at x equals 0. It has moved down 9, and so the horizontal asymptote is y equals -9. So my new point of symmetry is 0, -9. The x goes in the x spot, the y goes in the y spot. Okay, this one is not in good form. There should be another set of parentheses here, basically factoring out the 3. To see that it has been moved left 4/3. And so x equals -4/3 is our vertical asymptote. And then up 7, so our horizontal asymptote should be y equals 7. And so the point of symmetry would be -4/3, 7. And if you were to graph this, you would see a vertical asymptote at x equals -4/3. All right, so that's the point of symmetry. Find your vertical and horizontal asymptotes, and then fill in your coordinates appropriately. Okay, I'm going to skip max and min on an interval for just a second and go to intercepts because this will be a little more familiar. And so to find the x-intercept of any function, we've been talking about plugging in 0 for the y and solving for the x. We always write it as an ordered pair, x comma 0, whatever that x value is. Okay, it's important that you do that in this lesson because if you just write x equals, you could be talking about a vertical asymptote. We write vertical asymptotes as equations. We write x-intercepts as ordered pairs. And so it's going to be very important in this unit to do that. Okay, to find the y-intercept of any function, you plug in 0 for the x, and you just evaluate the function. You don't actually have to solve. You have to solve for this because you have to isolate x. Here, you're basically just number crunching. Okay, also write it as an ordered pair. X is 0, and then you're finding the y-coordinate. Okay, and so to find the x-intercept, we're plugging in y equals 0. And so that means the left side of my function is 0. And to solve for this, we need x out of the denominator, and so we would multiply both sides by x. Of course, 0 times anything is still 0. And so I'd end up with 0 equals 1. And so this has no solution, and so there is no x-intercept, which makes sense because we have a horizontal asymptote at y equals 0. And so if I plug in y equals 0, that's where the asymptote is. Okay, something similar happens with the y-intercept. Here we're plugging in x equals 0, and so my function would become 1 over 0, which of course is undefined. You can't have 0 in the denominator. So because we have an undefined expression, we ended up with no solution. Because 0 can't ever equal 1. Our variable disappeared and left us with a false statement. Here we're left with an undefined expression, and so also no y-intercept. Okay, and of course that makes sense as well because we have a vertical asymptote at x equals 0. This is our parent function, and so both of the axes have a asymptote. And so there's no way to have an x and y intercept when our function avoids both axes. Okay, here we could end up with one. Just picturing the graph, left 3, down 5. And then the reflection, I'd have a piece here and a piece down here. Okay, and so I can see that my y-intercept is going to be somewhere less than -5, and I can see that my x-intercept is going to be something less than -3. Okay, so to calculate it algebraically, starting with the x-intercept, we're plugging in 0 for the y. Okay, and so now to solve for x, we first need to add this 5 to both sides. And then x is trapped in the denominator, and so you can think of it as cross-multiplying if you want. We just need to multiply both sides by that denominator. So multiplying both sides by x plus 3. That would cancel and leave me with a 5 times an x plus 3 on the left and a -1 on the right. From here, you can distribute the 5 and then subtract the 15 and then divide by 5. Okay, and so x equals -16 over 5, which as a mixed number is -3 1/5. And so that matches what our picture is. It's a little bit past the -3. And so write your final answer as an ordered pair. I like the mixed number better for these. I very rarely like mixed numbers, but when I'm talking about a key feature, like a point, it's easier to understand what a mixed number is on the graph. All right, and then for the y-intercept, we are plugging in 0 for the x. And so that would give me y equals -1 over 0 plus 3 minus 5, which is -1/3 minus 5, which I'm going to go ahead and leave it in its mixed number, -5 and 1/3. Okay, and so looking at our picture, it's just past the -5 like we expected. And that would be our final answer. Okay, looking at this next one, starting with, let's just sketch it out. I think it's helpful to see what this could look like. So it hasn't been moved left or right, so my vertical asymptote is still sitting at x equals 0, but it's been moved down 9, so my horizontal asymptote is way down here at -9. There's no reflection, so we still have a piece in the left, or the first quadrant, and then we have a piece in this bottom quadrant. So it looks like our x-intercept is going to be pretty close to 0, but positive, and then our y-intercept is going to be pretty negative. Nope, we won't have one, because we have a vertical asymptote, and so it's just going to get infinitely close. And so we'll see if that matches algebraically. So to find the x-intercept, we plug in 0 for y and solve for x. So our first step would be to add 9, multiply both sides by the x, and then divide by 9. So x is 4/9, and so as an ordered pair, 4/9, comma, 0. And that is what we expected. Something small, but something positive. Okay, and then for the y-intercept, we're expecting not to have one. And when I plug in 0 for x, I get a fraction with 0 on the bottom. And so once again, that's undefined. That's an undefined. If you type that in your calculator, you'll get error. Desmos will actually say the word undefined. And so there is no y-intercept, just like we expected. Okay, for this last one, we can sketch it. We have a vertical asymptote at -4/3. So just before the -1. And then we have a horizontal asymptote at +7. We are still in quadrants 1 and 3 because there's no reflection. And so just looking at our picture, my x-intercept is going to be close to -1. My y-intercept is going to be above 7. Okay, so x-intercept, plug in 0 for the y, subtract 7 from both sides, multiply both expressions by that denominator, so -7 is getting multiplied by that 3x plus 4. That looks like -7, so don't write it like that. -7 is going to get distributed, and then we just have a 1 on the right. So -21x minus 28 equals 1. Add 28 to both sides, we get a 29. Divide both sides by -21, and we get -2921. As a mixed number, that would give us, it's bigger than 1, and then we would have 8/21 left over. So just past -1, which is exactly what we expected. You could leave it as an improper fraction if you wanted to. I just like to be able to approximate it on the graph. And then for the y-intercept, plugging in 0 for the x would give us 1 over 0 plus 4. 3 times 4 would, or 3 times 0 would just give us a 0, and then plus 7. So that gives me a 1/4 plus 7. And so I'm going to leave it as a mixed number, 7 and 1/4, which is just past the 7, exactly what we expected. All right, so the last part is the max and min on the intervals, which is usually the hardest part. And so before I summarize how to find this, I want to do an example. And so here we're finding the max and min on this interval. And so remember, your interval is always x values. We're restricting the domain. And so if I'm looking at the interval from -3 to 2, I'm just looking between these two vertical lines. So when I sketch my picture, I'm just sketching that interval. So we're just looking between these two lines. And so now when I graph my function, this is the parent function. So he still has a vertical asymptote at x equals 0. And I don't want to graph that point at x equals 0. And then a horizontal at y equals 0. He's got a point at 1, 1, and -1, -1. So looking like this, quadrants 1 and quadrants 3. Okay, and so if we're trying to find the max and min on this interval, there is not going to be a max because it's going to infinity in the middle of this interval. As it approaches the asymptote, it's going up to positive infinity. So there's no maximum. And then here, it's going down to negative infinity. And so there's not going to be a minimum. Okay, and so by sketching this picture and seeing that our vertical asymptote falls right in the middle of this interval, that means our function is going to be approaching both positive infinity and negative infinity on this interval. Okay, so there will be no max and there will be no min because it's approaching both positive and negative infinity. Okay, and so your steps to finding the max and min on intervals is first sketch the graph and clearly identify where this vertical asymptote is, okay? And then you're going to sketch the interval as vertical lines, just like I did, these gray lines. Okay, so let me color code this. So I graphed my vertical asymptote in red, this line right here, and then I graphed the interval as gray vertical lines. If the vertical asymptote falls inside, just like this example did, my vertical asymptote was inside, in between the interval, there will be no max or min. Don't even have to do any math. Okay, if the vertical asymptote falls outside, you just need to plug in each endpoint to figure out the max and min. Okay, and so looking at this next example, my vertical asymptote is at x equals -3. And so if I were to sketch where -3 is, I know this function has a vertical asymptote at -3. Okay, and then my interval is -1 to +3. Okay, and so here it falls outside. So if I were to sketch the rest of the graph, it has a horizontal asymptote at -5. And there's a reflection, and so it's going to be in quadrants 3, 2 and 4. Okay, quadrants 2 and 4 with my point of symmetry as the new origin. Okay, so this function is increasing on our interval. And so this will be our minimum, and this will be our maximum. Okay, and so our minimum occurs at the x equals -1, and our max occurs at the x equals 3. And so we just need to plug those in to figure out what the actual values are. So with my function, we have -1 over x plus 3 minus 5. And you can just put the negative on top. X plus 3 minus 5. And we are plugging in -1 for x, and we are plugging in the 3 for x. So here I get -1 over 2 minus 5, which I'll leave as a improper fraction, -5 and 1/2. Okay, and so that is going to be my minimum. And you can see that -5 is here, and -5 and 1/2, that makes sense. Okay, and then for my maximum, we get -1/6 minus 5, which is -5 and 1/6, which would be slightly closer, slightly above, and so that makes sense for our maximum as well. It's higher. This is more negative, this is less negative. Okay, looking at this next example, we're looking at the interval from 1 to 10. I'll go ahead and graph that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Interval 1 to 10. And then my vertical asymptote is going to be at x equals 0. It hasn't been moved left or right. So it does fall outside the interval. So I'm going to go ahead and graph the rest of the function. My horizontal asymptote is -9. I'm just going to call that -9. And no reflection, so we are in quadrants 1, oops, not like that. Quadrants 1 and 3 with respect to our new point of symmetry, our new origin. And so this function is decreasing on our interval. It starts here and is getting closer and closer to the asymptote. And so I can see that my maximum is going to be at x equals 1, is going to lead to the maximum. And then as it's decreasing, as it approaches the 10, it's going to be our minimum. That's going to lead to our minimum. Okay, so just plugging those in, I have x equals 1, I have x equals 10. Copy down the function, y equals 4 over x minus 9. And then replacing the x with 1 and 10. So here I get 4 minus 9, which is -5. So not drawn to scale. And so that would be my maximum. And then to find the minimum, I have 4/10 minus 9. 4/10 is the same as 2/5 minus 9. If we convert or get a common denominator, 9 is the same as 5/5. So -43/5. If you want to convert that to a mixed number, -8 and 3/5. And so getting closer to the -9, but not quite there yet. That's our min. Obviously lower than the max. Okay, for our last one, our interval is -2 to 4. And then our asymptote, remember this is bad form, is at x equals -4/3, which is the same as -1 1/3. So our vertical asymptote is just past, let me do better, just past the -1, -1 1/3. So this time our vertical asymptote does fall on the interval. We have a horizontal asymptote at 7, but either way, we can see that our function in quadrant 1 is going to approach, is going to approach positive infinity and is going to approach negative infinity. And so there is no max, no min. Okay, and so if you are solving this problem, I would honestly just figure out where the vertical asymptote is and see if it falls in this interval. It does, and then you don't have to waste any time sketching it. You can go ahead and jump to no max and no min. If it is in the interval, like here I found it to be x equals -3, and that does not fall between -1 and 3, that's when I would sketch it out and see what my max and min would be.